We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Okay, my feet are out. Okay, I'm out. Really looks funny out there. See my glove out there, Jim.
Jimmy 4, get back yet.
Okay.
Good morning, Gordo.
Good, how are you?
How does it feel for the United States to be the new record holder?
At last, huh? By cooperating together in these new realms of infinity.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11. Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you're listening to episode 53 of the Space Rocket History Podcast. And now, Gemini 2. You may recall from the previous episode, the U.S. had just completed the highly successful flight of Gemini 1. Now let's turn our attention to Gemini 2. When the Gemini management team met a week after the Gemini 1 mission on April 15, 1964, most of the group was comfortably optimistic. The current work schedule called for Gemini 2 to be launched near the end of August and Gemini 3 in mid-November. The schedule for both launches had a 4-week cushion to handle unforeseen problems. Let's take a minute to understand the purpose of the Gemini 2 mission. There were two main goals. The first was to demonstrate that the capsule could withstand maximum heat of reentry. In order to create the worst-case heating scenario, a suborbital flight was planned. The second goal was to further prove the spacecraft systems prior to the first manned flight. This is the way NASA explained the mission.
After the first successful flight, major emphasis was placed on the launch of the second spacecraft. Unlike the orbital mission, GT-2 was suborbital and would be recovered. As such, the primary purpose was to demonstrate that the reentry module would withstand maximum heating conditions of reentry. An ablative heat shield covers the larger diameter end, which enters the atmosphere first and bears the greatest thermal and pressure stress. Dish-shaped, it is manufactured from fiberglass honeycomb filled with silicon elastomer. The remaining outer shell of the cabin is covered with shingles of Rene 41, a heat-resistant alloy. The rendezvous and reentry section is constructed of a titanium alloy with outer shingles of beryllium. Beryllium is an element with the property of absorbing unusually high inputs of heat without rapidly increasing in temperature. A parallel purpose of GT-2 was to further qualify the spacecraft systems for the first manned flight. Electronic simulators were included in the flight to measure many elements of crew participation.
The major systems of the spacecraft were environmental control, electrical power, propulsion and control, guidance and navigation, communications and instrumentation, sequential systems, pyrotechnics, escape system, and the landing system. NASA provided a description of each system. We'll start with the environmental control system.
An important element of environmental control is the coolant system. This is, in reality, a thermal balance control system. For it not only cools the cabin, suits, and equipment, it also heats the cryogenically stored liquids, converting, for example, liquid oxygen to a gaseous state, which the astronauts can breathe. A coolant fluid is pumped from a reservoir through a closed-loop system. It flows through cold plates on which are mounted the electronic and electrical equipment, absorbing heat. It also flows through the space radiator. The space radiator is an integral part of the spacecraft structure in the adapter, equipment, and retrograde sections. It aids in maintaining proper temperature of the cooling liquid by causing it to lose heat in space. The environmental control system also furnishes oxygen to the cabin and pressure suits. In addition, it provides for waste management and supplies food and drinking water.
In addition to electrical power, the fuel cells might provide a source of drinking water.
Drinking water may be supplied as a byproduct of fuel cells, which will be the main source of electrical power. Fuel cells produce electrical power by uniting oxygen and hydrogen through catalytic electrodes. 2 such fuel cell batteries will be the main electrical source during the longer missions of 7 and 14 days. Silver-zinc batteries will supply supplementary and backup power. The fuel cells are in the adapter section. When this is jettisoned, the spacecraft switches to 4 of the backup batteries in the cabin section.
Propulsion and control systems were to receive a good test during the flight of Gemini 2.
Major elements of the propulsion and control system were tested by the flight of GT2. These were Orbital Attitude and Maneuver System, or OMS, Re-entry Control System, RCS, and Attitude and Control Maneuver Electronics, which conveniently shortens to ACME. The Orbital Attitude and Maneuver System will give the command pilot an onboard capability of making maneuver changes as well as attitude and velocity changes after separation from the launch vehicle. The system has 16 thrusters located in the equipment and retrograde sections of the adapter. 8 thrusters producing 25 pounds of thrust control the spacecraft in pitch, roll, and yaw. The remaining 8 thrusters, producing either 100 pounds or 85 pounds of thrust, control the spacecraft in the vertical, up and down, and horizontal, left and right direction. They also speed up or slow down the spacecraft. Using these, Gemini can make orbital plane changes as well as orbital altitude changes to effect a rendezvous and docking maneuver with a target vehicle. During the year, the OHM system was thoroughly qualified by ground test for flight in GT2. The command pilot jettisons the adapter prior to re-entry, and the OHM's thrusters are lost. He then switches to the re-entry control system to maintain attitude control. This has 2 independent systems. Each consists of 8 25-pound thrusters. The re-entry control system was qualified by a ground test program during the year. It would undergo a thorough flight test during the re-entry mission of Gemini 2.
Of course, the year he was referring to was 1964. The modular guidance and navigation system was controlled by a digital computer with a whopping 160,000 bits of random access memory. This number seems ridiculously small by our standards, but at the time, it was state-of-the-art.
The guidance and navigation system is packaged in modular units and housed in the spacecraft cabin and rendezvous and recovery section. It includes a general-purpose transistorized computer of the binary digital type, an inertial measurement unit, horizon scanners, an L-band radar for rendezvous and docking maneuvers, and a time reference system providing time to go for mission events, and a Greenwich Mean Time clock. The inertial measurement unit provides attitude data with either inertial reference from the inertial platform or Earth vertical reference from the horizon scanners. It furnishes attitude and velocity information to the spacecraft computer and to the console displays. Located within the right crew station, the computer has a solid-state random access memory capable of storing over 160,000 information bits. Both the pilot and ground control can feed new information into the computer, keeping it updated with the mission at all times. It furnishes data to the command pilot for his use in controlling re-entry and landing the spacecraft within close limits of a designated point. Another important function of the computer is to receive and process data from the L-band radar during rendezvous.
The communication system provided 3 methods for contacting the ground.
The Gemini spacecraft maintains contact with the ground through 3 systems: voice communications, beacons, and telemetry systems. Telemetry monitors both equipment function and the biomedical condition of the crew members. Over 300 separate measurements are recorded and monitored by ground receiving stations. Voice communication is maintained between the ground and the crew by high-frequency and by ultra-high-frequency transmitters-receivers. There are 2 systems, one of which is a backup. 3 types of tape recorders are included in the communication system: voice, biomedical, and data. There are 2 voice tape and 2 biomedical tape recorders in the cabin. They furnish a record of portions of the mission for later detailed study. A continuous record of systems performance is kept by the data tape recorders, which will be particularly valuable for intervals when the spacecraft is out of contact with ground receivers. On command over a station, data recorders will dump this information and begin re-recording with a clean tape. There are 4 beacons: a recovery beacon, which operates on the international distress signal during landing and recovery; acquisition aid beacon, primarily to help in tracking the spacecraft in orbit; and C-band and S-band beacons. The C-band beacon furnishes accurate tracking information to the ground stations from liftoff to jettison of the adapter. The S-band beacon is a backup system.
The sequential and pyrotechnic systems provided timing of key events and separation.
The command pilot controls critical events during the Gemini mission through the sequential and pyrotechnic systems. Chief among these mission events are separation of the launch vehicle and spacecraft, separation of the adapter equipment section, firing of the retrograde rockets as a backup after the clock initiates the signal, and deployment of the parachute landing system. All sections are separated by the detonation of pyrotechnic devices. The solid propellant motors of the retro rockets are ripple-fired by the sequential system at 5.5-second intervals when used for normal reentry, and salvo-fired for high-altitude aborts.
There were 2 possible scenarios for using the escape system.
There are 2 abort conditions, at high altitude and low altitude. At high altitudes, the command pilot shuts down the launch vehicle with the abort handle and waits 5 seconds. He then separates the spacecraft from the launch vehicle, initiates re-entry, and flies the spacecraft in. At the proper time, the parachutes are deployed as in a normal landing. At lower altitudes, the ejection seat is used for abort. Above 7,500 feet, the free fall of the astronaut after seat separation is first stabilized by a ballute, or balloon-type parachute. Successful ballute tests from 12,500 to 35,000 feet have been held. Indicated airspeed was 110 knots. 6 dummy and 17 human drops were made in this period. Ballute diameters of 3, 3.5, and 4 feet were tested. The 4-foot ballute produced the lowest rotation rate and was chosen for the flight configuration. The ballute separates at 7,500 feet, and the pilot's personnel parachute is automatically deployed slightly below 5,700 feet. It can also be deployed manually. The seat is manufactured by Weber Aircraft. Each seat is ejected individually by a rocket catapult actuated by hot gases that result from blowing the cabin hatches. Extensive testing of the seat ejection system was conducted throughout the period of this report. 3 types of tests were run: rocket sled tests at Naval Ordnance Test Laboratory, El Centro, California, simulated off-the-pad tests, and seat ejection from an F-106B aircraft. Although seat ejection was still in qualification testing during this report period, subsequently the system has been successfully tested under actual flight conditions from an F-106B.
The landing system used 3 parachutes.
Is the landing system. 3 parachutes are used during a manned mission: drogue, pilot, and main. The high-altitude drogue parachute is deployed by a mortar at approximately 50,000 feet. The drogue parachute has 2 functions. It stabilizes the reentry module and deploys the pilot parachute. The pilot chute separates the rendezvous and reentry sections from the reentry module. At the same time, it deploys the main parachute, which is first reefed to reduce the initial shock. After the main parachute is fully inflated, the spacecraft shifts from a 1-point to a 2-point suspension. This positions the reentry module in the proper landing position, with its nose 35 degrees above the horizon for landing in water.
Now that we understand Gemini's systems, let's return to the launch preparation for Gemini 2. The bright outlook that was prevalent in April turned dark in the late summer of 1964, when a series of natural disasters struck the Cape. First lightning, then hurricanes conspired to damage the second Gemini launch vehicle on Complex 19 to delay its flight long past the scheduled time. Even had the weather been perfect, McDonnell's difficulty in getting Spacecraft 2 ready to fly might have compromised the schedule on its own. Gemini Titan II was plagued by late deliveries, most notably the thruster systems from Rocketdyne and the fuel cell stacks from General Electric. This had slowed construction of the spacecraft during 1963. Also, parts had failed that had to be passed before they could be installed in the spacecraft, and modifications meant further delays. Spacecraft 2 could not begin its systems test until January 13, 1964. The Spacecraft 2 design engineering inspection was originally set for November of 1963, but had been postponed in the face of delays until February of 1964. In January of 1964, MSC, the Manned Space Center, formed a permanent design engineering inspection board to make sure that the spacecraft as a whole and each of its parts would do what they were intended to do, so that the spacecraft could, in fact, be expected to achieve its assigned objectives. Normally, the design engineering inspection for each spacecraft would fall between the end of manufacturing and the start of systems testing. But the DEI for Spacecraft 2 was a little late. The 9-member board convened at McDonnell on February 12th. Also present for the 2-day meeting were 50 experts from the Gemini Project Office and McDonnell, as well as another 50 observers from other MSC offices, NASA headquarters, and the Air Force. The board looked over the hardware and studied the records to see that each part either matched design specifications or was the subject of a proper waiver. A long list of minor discrepancies ended up as 22 mandatory changes, 4 conditional, and 10 to be studied. The first phase of spacecraft systems test went slowly, as problem after problem turned up. Troubleshooting problems and working out the required changes and testing the results all took time, which added to the delays. By mid-April 1964, Spacecraft 2 had become the pacing item for the second Gemini mission. In other words, the spacecraft was the furthest behind schedule. Being the pacing item was a dubious honor. You may recall on Gemini 1, the launch vehicle was the pacing item. Getting the spacecraft ready was now the crucial factor in meeting the scheduled launch date. This was not altogether a surprise. Remember, Spacecraft 1 had been little more than an instrumented shell, but GLV-1 had been a launch vehicle in every sense of the word. The Martin crew working on GLV-2 were performing tasks that had already successfully been completed with GLV-1, but Spacecraft 2 was the first fully equipped ship to go through the McDonnell plant, and its slow progress reflected that it was the first fully functional Gemini capsule. After the modules of the spacecraft had been mated, the second phase of systems test began on June 3rd. Further problems hampered testing into August. Whatever delays might have resulted, however, became purely academic after mid-August, when Florida weather dealt the first series of time-consuming blows to GLV-2. Now that we have covered some of the spacecraft problems, let's take a closer look on how the launch vehicle went through testing. At first, GLV-2 moved briskly through its test program despite some rough spots. At the outset, the second stage oxidizer tank was found defective and a new tank had to be built. Since the first stage engines were not yet installed, the delay was inconsequential. Martin Baltimore received all 4 tanks from Denver on July 12, 1963. Engines were late in arriving from Aerojet, but testing went ahead with non-flight first-stage engines. By the end of January 1964, GLV-2 had completed its horizontal test program. Early the next month, it was standing in the vertical test facility, and after 2 weeks of modification works, functional verification tests of subsystems began on February 21st. GLV-2 finished these tests by April 13th, in roughly 2/3 the time it took for GLV-1. It only took 1 week for electrical electronics interference test and 3 preliminary combined systems acceptance tests. These tests had taken a month with GLV-1. The formal combined systems acceptance test was run on April 22nd with no problems, and the results were approved by the vehicle acceptance team the following week. The dummy engines still had to be replaced, which took a month, but by mid-June, GLV-2 had been inspected and formally accepted for the Gemini program. Since spacecraft work was lagging, the booster's transfer to the Cape was postponed so Martin crews in Baltimore could complete some of the modifications that would otherwise have been made by Martin crews at Cape Canaveral. On July 10th, workmen loaded the booster aboard an Air Force C-133B aircraft, and by July 11th, both stages had been unloaded and secured. The Martin Cape crew worked a 2-shift, 5-day-a-week schedule to have GLV-2 ready for the spacecraft by mid-August. Everything proceeded routinely through July and into August, with only minor problems causing small delays. Of course, the spacecraft was still in St. Louis at the McDonnell plant. Its shipment was scheduled for August 1st, but had been postponed for 3 weeks. This made it impossible to reach Complex 19 before September. The Martin crew nevertheless prepared for the final test of the booster before its mating with the spacecraft and were almost finished on August 17th. But that Monday, a severe thunderstorm pounded Cape Kennedy. About half an hour before midnight, lightning struck Complex 19. There was no visible damage to the blockhouse, erector, or rocket, but that proved nothing about the status of the electrical and electronic gear. It was now highly questionable whether GLV-2 was fit to fly. NASA labeled the event an electromagnetic incident and demanded a thorough investigation. Inspectors from Martin Aerospace and the 6,555th Aerospace Test Wing found no signs of any physical damage, but they did locate a number of failed parts, mostly in the ground support equipment. This suggested that the complex had not taken a direct hit, but rather had suffered the electromagnetic effects or induced static charges of a nearby lightning strike. A test order issued on August 20th set the task to reestablish confidence in all launch vehicle and ground and facility systems and to determine that all degraded equipment was replaced and appropriate re-verification tests were successfully completed. They were given 2 weeks. The next day, Gemini manager Matthews flew in from Houston for an incident status meeting. A 3-man steering committee was appointed to oversee the efforts of the Air Force Aerospace and Martin work crews. 2 weeks seemed ample time to put things back in order. Most subsystems would have to be retested, and all booster systems, test equipment, and facilities would have to be checked out. Any equipment that might have been affected had to be repaired or replaced. After some consultation, NASA agreed that no airborne units from semiconductors ought to be retained. Once new units were installed, testing could begin again as though the vehicle had just arrived at the Cape. Before the work was finished, however, Hurricane Cleo brushed the Cape on Thursday, August 27th. The Martin crew had time to get the second stage down and under cover, but the first stage remained upright, lashed in place with the erector lowered. Cleo's winds were well below the upper limit that the booster was designed to withstand, but with the weather still bad on Friday, the second stage stayed in storage over the weekend. On Monday, the Air Force was getting ready to launch its first Titan 3A from the next complex, which hampered work on Pad 19 for most of the day. By 3 o'clock the next morning, however, the Martin crew had Stage 2 back in place atop the first stage. Further work was delayed by the countdown on the nearby pad, which ended at 10 a.m. Tuesday when Titan 3A blasted off. GLV-2's repeat of subsystem function verification test began on Thursday, September 3rd. By then, the Manned Spacecraft Center was just about ready to give up on GLV-2. The center proposed dropping it from the program and moving each of the other launch vehicles up a notch. GLV-3 would launch Spacecraft 2, and the flight program would lose one mission. The Air Force and the launch vehicle contractors strongly urged NASA to stick with GLV-2. After a thorough review of the effects of both lightning and hurricane, the measures taken to counter them, and the test results, had convinced the Air Force and its contractors that GLV-2 was still as sound as ever. Their case was solid enough to convert the skeptics. An Air Force spokesman concluded, based on technical considerations, Martin Marietta Corporation, Aerojet, and Aerospace Corporation recommend to fly GLV-2. NASA agreed and the work went on. Testing had scarcely begun, however, before nature intervened a third time. Hurricane Cleo had struck only a glancing blow, but Hurricane Dora was aiming straight for the Cape. As Dora approached on September 8th, Martin workers raced to get both stages of GLV-2 down and safely under cover in a hangar. Wednesday was a day of waiting as Dora passed by. On Thursday, Dora was no longer a threat, but Hurricane Ethel was heading for the Cape and due to arrive by the weekend. GLV-2 stayed under wraps. By Monday, September 14th, the danger was past and GLV-2 was back in place before the end of the day. The rest of the week was largely given over to replacing semiconductor units and to a thorough inspection of the booster and launch complex. Testing resumed after the weekend on September 21st. And on that day, the spacecraft finally arrived in Florida. At last, the launch vehicle and the Gemini 2 capsule had reached the Cape. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.